can you see the screen? I just need the...
Yes.
Okay, perfect. All right, so today I'll be telling you about human cognition and human-robot interaction. So the talk maybe will be slightly different from what you have heard so far in general with respect to the other talks during the school. And that is because I'll be talking more about humans than about robots, but humans in human-robot interaction. So my background is cognitive neuroscience, and therefore I'm more interested on the human side of human-robot interaction. But I'll try to convince you throughout my talk that there's a very strong link between cognitive neuroscience and robotics, and the link is bidirectional, and the lessons that we can learn one from the other are very important. And therefore, even though we are studying humans in human-robot interaction, we can provide some lessons to robotics. So yes, as I already mentioned, I'll be talking about the link between cognitive neuroscience and robotics, and what those two disciplines, how can they inform one another. So first, robotics for cognitive neuroscience. So what can robotics bring actually to my area of expertise and the field of cognitive neuroscience? Well, first of all, this is exactly what we're doing in our lab. We can use robots as sophisticated experimental apparatus for understanding the human cognition, the human brain, in more ecologically valid experiments, as opposed to something that has been used throughout history of cognitive neuroscience and cognitive psychology, namely stimuli presenting to participants on the screen, very abstract, very remote from our daily activities. On the other hand, when we have embodied robots like the one you see on this picture, what we can do is translate experimental paradigms from cognitive psychology into more interactive protocols. And for example, look at attentional mechanisms, how they work in this kind of more real life scenario with embodied presence of another agent. Sure, it's still an artificial agent, it's not another human, but artificial agents, meaning robots, give us the advantage of having still experimental control over the behavior while having more ecological validity. So this is one way that robotics can influence cognitive neuroscience and give us some information about human brain mechanisms in real, more, let's say, real world situations. There's another way, and I'm pretty sure that you've heard about this, perhaps from Professor Giulio Sandini. I saw that he was speaking on the first day of your school. Robots being kind of embodied models of human cognition. And through this kind of modeling that takes into account also embodiment, we can really understand how the human brain works, because models are kind of new modern ways of theorizing about the brain. So through modeling, we try to also understand humans and how the human brain works. So this is another way how robotics can influence cognitive neuroscience. Now, on the other hand, we can also learn something in robotics from cognitive neuroscience. So through testing with human participants, how the way we're doing that in our lab, various mechanisms of human cognition, we can provide guidelines on how robots should be designed, how should they behave in human-robot interaction to be most suitable for the humans, so that the interaction is most intuitive, and also something that is quite important, that the robot behavior taps on the same mechanisms that the brain has developed for human-human interaction, so that we can reuse the same sort of mechanisms of our brain that we use in daily interactions with other humans for interaction with robots. And this is not a trivial task, because there's so much going on when we were interacting with others. And in order to model that and have actually similar behavior on the robot, it's really, really tricky. And this is exactly what my lab is doing. So some robot designs, I will be talking throughout this talk today about some robot design principles for this intuitive human-robot interaction based on human-robot interaction studies. So think about a scenario like this one, right? It's a very casual, mundane, in a sense, scenario of our daily activity. We're in a pub, ordering a beer, and the bartender is handing us the beer. This is an extremely rich in terms of cognitive mechanisms involved scenario. So we do it super effortlessly, and we don't even realize how much our brain needs to process in this kind of scenario. So what is happening here, as you can see, there's a lot of gaze contact there. Through gaze, there's a lot of information being conveyed to our interaction partners. So there's information about where one of the interaction partners is looking, and therefore where the person is attending. This person is receiving this signal, and based on this signal, needs to plan her action accordingly to actually not drop that glass on the counter. Then there's action planning. She needs to plan her action according to how he's actually handing over the glass. So she needs to receive the glass in an appropriate way. And the way it's being done is that as she's planning her action, she's reading out the intentions of that person, the trajectories, and so on and so forth. So this is a super simple task that our brains do all the time, but it's extremely complicated in terms of how many processes are involved. So thinking about a scenario like this, if you want to have a robot here instead of the human, you need to really think well on how to design that robot so that the human can read out similar amount of information and can plan action accordingly. So this is our scenario that we sort of, mock this real life scenario with a robot. And this is an illustration of the methods that we're using in our lab. So we are embedding our participants in these kind of daily life situations and with the robot. And as they're doing their task, we're measuring their neural activity with an EEG cap here. So you see here that this is Brain Products EEG system. We're also measuring, so she's wearing those funny glasses, but these are actually eye tracking glasses. As she's doing the task, we can track her eyes to understand where her focus of attention is and correlate that with the brain activity. And then you might wonder, is like, why is she having a keyboard here? Additionally, this is just, again, for illustration purposes, but as she's doing this task, we often additionally give an additional task in order to be able to measure her performance. So like, for example, how fast is she able to detect certain signals from the robot or here from being presented on the screen. So we're measuring reaction times, error rates, and how those behavioral measures, again, relate to the brain mechanisms. So this is just to illustrate how we are working in the lab and what sort of information we can gather from this kind of methodology. All right, so first I'll be talking quite a lot about gaze. Gaze is very, very important, as you know, signal in daily interactions between humans. And I already pointed out to you in this scenario in the pub that through gaze, we convey a lot of information and our brain does it quite automatically. But think about so we all know that gaze is important. We all know that, for example, mutual gaze, looking into the eyes of the other person, is an extremely strong signal, right? But we also know that it has to be timed well, right? So I'm pretty sure that most of you have this experience of someone gazing into your eyes for too long or not looking into your eyes at all. And then the interaction is kind of strange, right? So our brain has learned how much is the sufficient and appropriate time. Throughout lifetime, we have learned that. By the way, neurotypical brains have learned that. There are cases like individuals diagnosed with autism that have actually problems in learning these kind of mechanisms. But okay, if I ask you, so we know how to do this, but if I were to ask you, okay, so how long is actually an appropriate time? Is it 500 milliseconds, 1 second, 3 seconds? I'm pretty sure you wouldn't be able to tell me, right? So intuitively, automatically, we do it, but we don't know explicitly. So if I am to provide guidelines to a roboticist, how long should the robot gaze into the eyes of the interaction partner for, I wouldn't be able to tell unless I do the studies that we do. And with this example, I just wanted to point out that most of our work is targeting those kind of implicit automatic mechanisms that we often are not able to then verbalize and explicitly report. So gaze direction, mutual gaze, I will tell you about a series of studies that we've run in looking into how attention of your interaction partner is, so attentional focus is, let's say, modulated by the gaze direction of the robot in this case, or of another interaction partner in the case of a human-human interaction. So this, let's say, attentional focus, orienting of attention in response to gaze, something we do all the time. So when someone looks to a side, it would be much easier for me to show it to you if I were there in person. But I'm pretty sure that you get the point if I tell you that if someone looks to the side, your attention also goes there because there's maybe something interesting there in the environment to look into. And this kind of orienting of attention in response to gaze has been operationalized in the laboratory setup and has been called the gaze cueing effect. And what is the gaze cueing effect? It's based on classical Posner cueing paradigm. This is a very old psychological paradigm, attentional paradigm, where typically the participants of an experiment are cued with directional cue. In this case, traditionally it was an arrow, for example. And the idea is that first you present an arrow to participants and you assume that participants' attention would be oriented to where the arrow is pointing. And then you present a target letter. It can be a letter or another stimulus, either in the same location or, sorry, this is actually a mistake. This arrow should be pointing still to the right, but you actually present the target in the opposite direction, opposite location. So when you validly cue the target, it's very easy for participants to discriminate and detect the target and, let's say, respond to it. So typically participants have a task of just respond to the identity of the letter. Is it a T or an F? And you have to press a button, T or F. And it's much easier for them to do this when the letter is presented in the same location where their attention has already been, as compared to the invalidly cued situation when the cue directs your attention to one side, but the letter is presented on the other side. In the invalidly cued situation, what you need to do is like shift attentional focus from one location to the other, and that costs time. And that is something you see when you compare these two conditions in terms of reaction times, for example. These reaction times would be slower. Now, why am I telling you all this? This is because you can actually make it more social. So instead of presenting arrows, you can present gaze, like, so again, a directional stimulus, but this time it's gaze. And this time I got the valid and invalid right on the slides. So here you have a validly cued target. The gaze is looking to the side where the target will be presented. And here the gaze is directing your attention here, but the target actually appears on the opposite side. So you need to switch your attentional focus, and that costs time. So in the case you see difference between these two conditions in reaction times, that means that attentional focus has been attracted by the gaze in this case. So you can implement that in a human-robot interaction and look at whether the robot's gaze is actually able to attract attention and guide attention of our human participants. Now, this effect is very much dependent on very many factors, and they are very, very subtle. So, for example, the timing, how long you present the gaze for, or what is the time between the gaze and the target presentation, the onset, the stimulus onset asynchrony, that all matters. And therefore, it's something that needs to be really studied systematically in order to implement this mechanism on a robot. So let me show you how we implemented this effect in a gaze cueing study with a robot. But before I get there, I wanted to mention one more thing. What we've been interested in is not, also the gaze cueing effect, but in relation to mutual gaze. So I was telling you earlier that mutual gaze is an important signal. Now the question is whether a mutual gaze with a robot is actually something that is as important as mutual gaze with a human, and how does mutual gaze affect this gaze cueing effect? So in addition to this manipulation of validity that you see here, we added a manipulation of mutual gaze. In one condition, the robot would gaze at participants first, and then do the directional cueing, and in another condition, it would gaze away and also do the directional cueing. So let me illustrate that with a video. So you see the robot is here between two screens. Now this is eye contact or mutual gaze, and now directional gaze. In this case, the idea is that you attract more attention, maybe more engagement with mutual gaze, if at all, with the robot, and then you can measure that with the validity effect. Here you have the condition of no eye contact. The robot looks down. It's much more clear when you're actually seated in front of the robot as compared to the video. And then you have the validity effect again. All right, so this is how the experiment looks. And these are the data. What you see here is the reaction times to the targets that are presented on the lateral screens. And if there is a difference between the valid and invalid condition, as you might remember, that means that participants engaged their attention with the robot and followed the robot eyes with their own attentional resources. And this effect is there when the robot first looked at participants, but not when the robot looked away, which is quite interesting, because that means that if you want to engage attentional focus of participants, the eye contact with the robot is actually important. So you should make sure that you engage participants first in an eye contact before you do other manipulations. Now, as I said, this is a little bit more complicated than that. I don't want to get into details of this because this becomes too complicated. But what matters is the timing quite a lot of both the mutual gaze and the directional cue, and how valid was the cue. So in this case, in these data that I'm showing you, the robot was valid 50% of times. So it gazed 50% of times in the location where the target would appear, but you can also do a different manipulation. So the robot can, for example, be misleading, right? And can direct your attention in the opposite side more often, and so on and so forth. Anyway, what I just want to say is that the two factors of, let's say, validity of the robot, so how reliable it is in its behavior, and the timing of all these events in the experiment are quite crucial for seeing various attentional effects. Now, this kind of objective measure of attentional focus have been paralleled by subjective reports. So we also asked our participants to rate how engaging was the eye contact with the robot, and they rated overall that eye contact was much more engaging than no eye contact. And here what we plot is different blocks. So basically, participants had a block, like a series, let's say, of trials where the robot was engaging in eye contact, and a series of trials where it was not. And then what you see is that whenever you see an N, there was no eye contact, or Y for yes, eye contact. And you see that whenever there was eye contact, the ratings went up, and in the blocks where there were no eye contact, the ratings for engagement went down. So that shows that subjectively, it's also experienced, eye contact of a robot is experienced, it's much more engaging. And we also ran an eye tracking study with the same paradigm, and we looked at fixation duration, so participants' eye movements during this task, and we looked at fixation durations during eye contact or no eye contact condition, and they fixated longer on the face of the robot in the eye contact condition, as you see here in this plot. And then finally, we also run an EEG study to understand the mechanism behind this. And we looked at the period when the robot was gazing at participants or not. And we looked at, we did a time frequency analysis, and we looked at the alpha frequency band, and we saw a difference in this cluster here of electrodes between no eye contact and eye contact condition. And actually, there was more desynchronized alpha in the eye contact condition. Now, then we looked into literature what actually desynchronization of alpha activity means in literature, and it has been found earlier as a marker of engagement. So our EEG data confirm subjective reports and the eye tracking data showing that indeed the eye contact with the robot is more engaging. So the take-home messages from these studies is that the human attentional system is sensitive to the robot gaze direction, and therefore similar sensitivity might need to be modeled on the robot because it's always mutual, right? So if I have a sensitivity to your gaze, you should display very similar sensitivity to my gaze. But again, this is quite complicated because there are various factors that are at stake here. So one needs to model these mechanisms with caution. Now, as I was actually speaking now, I was thinking, oh, maybe it sounds like trivial. Sure, mutual gaze is important. We know that it's engaging, and it is in human interaction case. But think about it. I mean, the robot is just a machine. The eyes are just two cameras, and participants are perfectly aware of that. They know that this is just a machine. We actually explain to them that you'll be interacting with a robot that is just a stupid device there. And yet, the same mechanisms are evoked in a human-robot interaction as in human-human interaction. So that means that a robot designed the way ICAP, so I wasn't mentioning this here, but I'm pretty sure you're familiar with ICAP. ICAP is a humanoid robot designed and developed here at our institute. The way ICAP is designed and the way those cameras are actually embedded in the face do hijack, in a way, our brain mechanisms that we developed for interaction with other humans. So this is quite striking because if you zoom out a little bit and think about it, it's actually not to be taken for granted that a robot machine with two cameras would make our brain respond to it as if it was a human face. And if you think about it this way, then actually it's not as trivial as it seems. All right. Now I wanted to continue with the gaze topic and talk about sensitivity to gaze in social decision-making processes. This study was kind of building up on the previous studies in terms of mutual gaze, and it was a really fun study to run for participants. So here what we have done is we adapted kind of something that is called a chicken game, a game where two opponents are playing against one another. So our participant and ICAP against one another. They have a screen positioned horizontally in between them on a table. And each of them has a simulated car, and the cars go towards one another, right, at the beginning of the trial. And they go towards one another up to a point where they reach this kind of central area, and that's when everything goes blank. So the screen goes blank, and your task is to decide whether you want to continue with your car going straight ahead or you want to deviate. And now what happens is that if you go straight ahead and the car and your opponent also goes straight ahead, the cars crash, you lose a lot of points. Here's the payoff matrix. You both lose a lot of points. Now, if you deviate, but your opponent goes straight ahead, you're the loser, and vice versa. Okay, so the reason why it's called a chicken game is that you should not chicken out. You should take a bit of a risk and but not too much, right? Because then the question is like, what will your opponent do in this game? Now, so it's kind of like a poker situation where you have to bet on your opponent. Now, the most important manipulation for us was that as participants were making their decision, so when the screen went blank, the robot either looked at them or looked away. So again, the mutual gaze situation. And we were interested, I already mentioned, in this kind of poker game situation where as you're making your decision about your next move, the opponent looks you in the eyes. What does that do to your cognitive processes? Does it help or does it hinder your strategies? Now, this gaze manipulation, the mutual versus averted gaze, was done in between subjects design. That means that one group of participants saw mutual gaze on 70% of trials, and the other one on only 30% of trials. This is because we wanted to control for the frequency of how often actually you see one or the other, so that whatever effect we get is not because of frequency, but actually because of the mutual gaze per se. So this is how you'll see the experiment. Here are the cars going towards one another. Now everything goes blank and you're supposed to make a decision. And as things go blank, now the robot you don't see right now, but the robot would gaze at you or gaze away, and then you'll see your points, whether you lost or won. And as participants were playing that game, we were measuring their EEG as well. So we wanted to see the neural activity. Okay, these are the behavioral data. So what we observed is that, first of all, people were slower in the mutual gaze condition as compared to the averted gaze. So these are our two conditions of interest. And that was independent of the group. So as you might remember, I told you that one group of participants saw mutual gaze 70% of trials, the other saw 70% of averted gaze. And independent of the frequency of exposure, let's say, to the mutual averted gaze, they always responded slower. So that already tells us that in this case, the mutual gaze is hindering participants to some extent because they're slower in making a decision. There's some sort of a conflict that they're solving in their brain as they're doing this task. Now, we looked at EEG in the same period again of averted versus mutual gaze. And we looked at alpha again, alpha bands in different, let's say, chunks of time within the period of gaze manipulation. And this time we saw higher synchronization of alpha activity in mutual gaze compared to averted gaze. Now, what does that mean? Higher synchronization is a different effect than the one that I showed you before. Higher synchronization of alpha in literature is interpreted as the need for suppressing irrelevant stimulus in the environment. So our brain is trying, in this task, is trying to ignore actually the gaze of the robot because they know that it might be distracting. They're trying to ignore it, and that costs an additional mechanism of the brain, which then results in longer reaction times, as you have seen in my previous slide. So in a situation where you need to focus on your own performance and make the best kind of decision in terms of strategic games, social robot is not a way to go. If by social, I mean engaging in a social kind of signal, social interaction with the mutual gaze. It's distracting and it's hindering our performance. Now, this is also another very interesting result from the study. We looked at the strategies that people took throughout the trials. They were implicit strategies because when we asked them, like, did you have any strategy to solve this task, they were usually telling us that they didn't have any strategy. At first, they thought maybe that the mutual gaze is informative with respect to the robot's choice, but then they realized it wasn't, because it wasn't actually. And so it's an implicit strategy, but what you can look at is the series of responses that people do, and you can classify them in these three strategies: win, stay, lose, shift, meaning that if I win, I do the same next time. If I lose, I shift my strategy. Tit for tat or stay, shift, imitation. Tit for tat means I do the same as my opponent, and stay, shift, imitation means that I imitate what my opponent did in the previous trial, right? Now, interestingly, this is the optimal strategy. The win, stay, lose, shift strategy is the optimal in the game, and it's also the strategy that the robot was programmed with in 80% of the trials. Why 80? Because we wanted to make sure that it's not going to be too obvious for participants, and in the remaining 20% of trials, it was behaving completely randomly. We asked participants whether they noticed any strategy in the robot, and they didn't. So the most optimal strategy in this game was chosen more often, again, in the non-social condition, which tells us again that the social condition was actually impairing participants' performance also in terms of strategy. So not only in terms of time that they took, but also in terms of the choices that they made. So yes, robot gaze, from this study, we know that robot gaze can act as a strong social signal. We knew this already from the previous series of studies, but in this case, it can be distracting and it delays our response times, makes us choose suboptimal strategies in a situation where we need to be as efficient as possible with respect to our own individual actions, and engages suppression mechanisms of the brain. So this tells us that social robots are not always beneficial for human performance. And I would like to stress this point because there's this general idea that we should always create robots that are super social and friendly and evoke all these, social mechanisms in us. And our data show us that it's not always the case. It very much will depend on the context. So if you think about I don't know, a context of a social robot that is supposed to be there helping the elderly and maybe, reminding them of taking medicine. So there has to be like some sort of a rapport created between them and some sort of a relationship in order to achieve the results of like the elderly person following the recommendations. Then being social is probably great. But if you think about, I don't know, flight control tower or any situation where I have to really focus well on my task and I cannot make mistakes, I have to be very efficient, and I have a robot next to me, it should not be social because that will be distracting for me. Therefore, maybe these additional social mechanisms are not desired in a situation where individual performance needs to be prioritized. Okay, then the next piece of work is about, again, sensitivity of the human brain. So I named it all like, what is our brain sensitive to in terms of robots' behaviors? I'm focusing on the gaze. So I talked about directional gaze in the first studies, then the mutual gaze and decision-making. And now in this study, we reversed the roles in the gaze cueing study. So this time the participant, instead of kind of following the robot gaze, the participant will be the one who will be gazing first to one of the locations, if you remember the Posner task. And then the robot will either be following or not participants' behavior. So here in this task, so it's just really reversing the roles. If you remember in our previous studies, the robot was gazing to left or to the right, and then we looked at whether participant focus is also to the left or to the right, following the gaze of the robot. Here, the participant is choosing at their own will one of the sides, and then the robot, since we have an eye tracker here, we're sending the commands to the robot to either follow our participant with its gaze or not. So this is how the experiment looks. Her task is just, there are two stimuli like toys on one screen and another one on the other screen, and her task is just to choose whichever one she is interested in. So let me just demonstrate this. You don't see, now you'll see how the robot is actually following her gaze. So she's just saccading to one of the screens. Now you see her saccade. So this line and the circle are showing where her saccades are, and the robot is either following or not her gaze. And just now it's clearly that it's following her gaze. Now we did two conditions in this experiment. In one condition, the robot was we called it Jimmy, was following our participants' gaze in 80% of trials. In the other condition, it was following our participants' gaze only in 20% of trials. And our dependent variable in this experiment was the time of the return saccade to the face of the robot. So kind of re-engagement, because the participant looks to one of the sides first, and then needs to return back to the face of the robot. And this time of returning back is a measure, again, of engagement with the robot. So we look at this time as our dependent variable. And what you see here is that the effect is mainly in the condition when the robot was mostly contingent, so mostly looking at the same location as our participants, and participants returned to the face of the robot faster as compared to when the robot followed their gaze as compared to when it unfollowed their gaze. So they were sensitive to this kind of contingency of the robot movement. In the case of the robot not following in general our participants, there was no effect. So this, what seems here to be a difference, was actually not significant statistically. In addition, we asked participants about rating anthropomorphism and likability, which robot they liked more. For anthropomorphism, we didn't find any differences, but we're not surprised because I mean, it was always the same robot that just had 2 different names. But they liked the robot that was contingent under gaze more. So the contingent behavior of a robot does play a role in engagement and anthropomorphizing, less so maybe. With, well, let's say with the same robot, it was hard to find this effect, but we found this effect in another study where we had this only screen-based stimuli. And one take-home message from this is that robots should display contingent behaviors towards our participants or whatever users in various contexts, because again, our brain is very much sensitive to that, whether other interaction partner is responding to my sort of gaze behavior. However, this might also depend on the context. So we need to be careful. Again, this is future work that we haven't done so far, but again, as in the previous study, it might very much depend on what the participant actually needs to do. Whether we want to have a social robot or not will depend on the context and on the task. Okay, and then the very final study on gaze is a recent study that we've run in our lab, which is really interesting, I think. This is a study that was modeled after a whole series of studies in developmental psychology first, and then animal studies with primates, with monkeys. Here, the idea is that we are somehow sensitive to what we call means to goal efficiency of our actions. So if you, let's look at this drawing here. If you're reaching for this toy, right, the most, let's say, efficient way to reach is this way. This is not so efficient if you're going like this, if there's no obstacle. Of course, if there's an obstacle, this is an efficient way of reaching the toy. But in this case, and when there's no obstacle, this is an inefficient way of reaching the toy. And this kind of idea of sensitivity to means to goal efficiency has been implemented first with, as I say, within developmental psychology work with toddlers, and then with monkey studies. What has been observed is that when you violate the means to goal efficiency, so in case of this kind of incongruent action when there's no obstacle, when you violate this through the actions, the observer and toddlers as young as 12 months old show longer looking times at this, let's say, incongruent action, so the one that violates this efficiency principle. And this tells us that already very small children are very sensitive to efficiency of our actions. Now, this has been then replicated with monkey studies showing very similar effects, so also longer looking times at incongruent actions. But there was something additional in the monkey study that was very interesting, not reported in the toddler studies, is that when the actor violates the means to goal efficiency principle, the monkeys not only look longer in general at the action space, but they also look more towards the face of the actor. What does that mean? They probably look in the face because they're trying to understand what is going on. They're trying to look for additional cues to understand this strange behavior. And this is quite interesting because that will tell us that if we see a similar effect with the robots, participants probably attribute certain intentions to the robot that they try to figure out from their face. So we implemented this with the ICAP robot. We implemented the same design. Here you have the occluder. Unfortunately, due to robot constraints, we couldn't do this action that is over the occluder, but we had to do it around the occluder in the, let's say, efficient action so from the side, and we have the same principle, like efficient or inefficient actions depending on whether there's an occluder or not. There's another part of the story that I don't want to go into, that there's a familiarization phase, so you kind of prime participants into certain like efficiency of the movement. This is just done to control for various factors. If you're interested, we can discuss that in the discussion. But basically, the most important point is the data, as always. And we looked at the region of the face of the robot, and we looked at the looking times, so fixation duration on the face, depending on whether the action was efficient or inefficient. And indeed, participants looked at the inefficient action longer than in the efficient action. So it's the replication of monkey studies that were done with human actors. In our case, it was adult humans observing the robots. So again, very interesting, because that shows that we're expecting from the robot to sort of display similar principles in terms of action efficiency as we would expect from a human. And if that is violated, that principle is violated, we look for additional cues to disambiguate this effect. Humans do show sensitivity to means to goal action means to go action principle, and therefore movement trajectories of robots need to follow similar principles to those of humans. And then I think, I don't know how I went with time, I'll maybe present this last study because it's a fun one, again with nonverbal Turing test, and I guess I'll leave some more time for discussion, so later on. So sensitivity to human-like variability in behavior. This is, again, another characteristic of human behavior that is very critical, and we need to take that into account when we're having our robots' behaviors, modeling our robots' behaviors, is that humans are super variable, and it's very, very difficult to have the same fixed type of movement across, for example, many trials. So the way, I move my hands now, and if you ask me to do again the same movement, it will be slightly different. It will be slightly different in time, in trajectory, and there's no way to achieve with a human the exactly same type of movement, even with gaze, with saccades. And so the question is whether our brains are sensitive to other people's variability, especially if it's very subtle, and especially when it's about timing. So this is something we investigated in our nonverbal Turing test, where our participants, so we were really interested in basically extracting just the timing parameters from very, very simple behaviors, meaning just key presses, and see if there's some sensitivity of the observer's brain to that kind of variability. So it's not large scale movements, it's just key presses. And what we've done here is that we had social Simon task. I won't go into details of the task also for the sake of time, but what I want to just explain to you is that we had two dyads. So one dyad is a human robot, let's say dyad. They're seated simultaneously, but in two different cabins. So we had two iCabs and two participants always invited for the task. And they are doing a very simple task together with the robot. So on the screen, they will see stimuli that are either green or red. And one member of the dyad is supposed to quickly, as fast as possible, respond to red. The other one is supposed to respond to green. So as simple as that. Okay, the important manipulation for us is that this robot can be either pre-programmed, and I'll tell you how it was pre-programmed in a moment, in terms of the timing of the button presses, or can be controlled by the other person seated in the other room. So the question here is whether this person will be able to detect when is this robot actually pre-programmed and when it's controlled by the other person. The only information that this person has is the distribution of reaction times across trials, because keep in mind that it's a super simple task. We just need to respond very fast to green or to red, and that's it. So you can only observe the robot across trials and see how it was responding across those trials with what sort of distribution. Of course, we don't tell this to participants. We don't tell them what they should pay attention to. They should just do the task and try to guess when was the robot controlled by a human or when it was pre-programmed. So this is just to illustrate, you see, these are the stimuli, super simple, and one of them needs to respond either the human or the robot responds depending on the color, and the robot either does it in a pre-programmed manner or is in real time actually controlled by the other human. So this is how we program the robot to behave in the computer conditions, so the pre-programmed case. We actually took the distribution of reaction times from human data. So we took the mean plus minus the standard deviation that we observed in human data. And the idea was to have a uniform, so to sample the robot reaction times from a uniform distribution from this mean and standard deviation. I lost seeing you. I hope you still hear me because I cannot see you anymore. Hello? Hello?
Can you hear us?
Yes, I don't see you, but you can hear me, yes?
Let me check. So now you can see me?
I can see you, yes. That's already good. As long as you can hear me, that's good. I'm almost done. Maybe that was a signal, but this is my last study I'm presenting. Okay, great. You can hear me.
I will unplug everything. But anyway, we are running out of time.
Yes.
Okay.
Yes. This is the last one. Okay, so I just want to show you the two distributions. So this is a pre-programmed distribution. This is the human-controlled distribution. And the question is whether people would be, observers would be actually sensitive to this kind of human distribution. And the answer is yes. In their Turing test question, they were actually above chance in detecting the human, while in the computer case, they weren't able to tell whether it was a computer or a human. So in a sense, the computer here passed the Turing test because they weren't able to tell. But the important thing is to notice that they have a sensitivity to this human-like behavior, again, without being able to tell what was the hint they based their response on. Okay, so humans have sensitivity to human-like behavioral variability, even with just subtle hints. And this variability within human-like range, even with different shape, blurs the distinction between human and machine. So the interim, which will actually be my final summary, I just want to say here that humans have sensitivity to robot gaze, whether it's mutual or averted. This affects attention, engagement, and cognitive control. Contingency in robot behavior, so the eye movements of the robots that are contingent or not on the human behavior, the means to goal efficiency of robot movements, and human-like temporal variability. And all these factors need to be taken into account in robot design. And with this, I will finish here. I have more slides, but I don't want to keep you too long. So with this, I would like to thank you very much for your attention.